Welcome to G Fun Facts Online. Today we're talking about cosmic timekeepers. These are relics from a bygone era, celestial messengers that have unraveled the 4.5 billion year history of our solar system. We're talking about meteorites. They aren't just rocks that fall from the sky. They are the fundamental clocks that scientists use to date the very origins of the sun, the earth, and everything in between. The overwhelming consensus from decades of meteorite analysis is that our solar system is approximately 4.567 billion years old. This isn't a guess. It's a figure derived from the meticulous, cross-verified dating of the oldest materials we have ever found. But why do we need rocks from space to date our own planet? The problem is that Earth is geologically alive. Constant processes like erosion, volcanism, and plate tectonics have been churning and recycling its surface for billions of years, effectively erasing the evidence of its earliest history. The oldest known mineral grains on Earth are about 4.4 billion years old, but these are incredibly rare. To find a truly pristine record of the solar system's birth, we have to look up to the time capsules that have remained largely unchanged since their formation, meteorites. To understand how meteorites work as chronometers, you need to know that they come in different flavors. They're broadly classified into three main families: stony, iron, and stony-iron meteorites. Each one tells a different part of the story. Let's start with the most common visitors, stony meteorites. They make up the vast majority of falls and are mostly silicate minerals, similar to rocks on Earth. But they are split into two groups that are crucially different: chondrites and achondrites. Chondrites are the most important type for dating the solar system. They are considered primitive because they have not been melted or significantly altered since they first clumped together from the dust of the early solar nebula. Their defining feature is the presence of chondrules, which are tiny, spherical grains of silicate minerals. These formed like little molten droplets in space, before being swept up into the asteroids that became their parent bodies. Because they are so primitive, chondrites preserve the original chemical and isotopic recipe of the early solar system. Some of the most primitive, called carbonaceous chondrites, even contain water, sulfur, and a rich variety of organic compounds, including amino acids. This is what gives rise to the incredible possibility that meteorites may have delivered the essential ingredients for life to the early Earth. In stark contrast, we have achondrites. The I in their name means without, and they lack the chondrules found in their primitive cousins. This is because they are fragments of larger celestial bodies, asteroids, the Moon, or even Mars, that were big enough to have undergone differentiation. Differentiation is the process where a planetary body heats up and melts, causing heavier materials like iron to sink to the core and lighter silicate minerals to form a mantle and crust. So, achondrites are essentially igneous rocks from other worlds, giving us direct samples of the crusts of other planetary bodies. Next up are the iron meteorites. As the name implies, they're almost entirely made of an iron-nickel alloy. These are the remnants of the metallic cores of large asteroids that were shattered by ancient impacts long ago. When you cut, polish, and etch an iron meteorite with acid, many reveal a stunning crystalline structure called the Widmanstätten pattern. This unique crisscross texture is formed by the incredibly slow cooling of molten metal over millions of years, a process that simply cannot be replicated in a lab. Seeing this pattern is a definitive sign of an extraterrestrial origin. They give us invaluable insights into the formation and composition of planetary cores, including our own. Finally, we have the rarest of the main types, the stony iron meteorites. These are a beautiful mixture of roughly equal parts iron-nickel metal and silicate minerals. The most striking subgroup is the pallasites. They contain crystals of the olive-green mineral olivine embedded within a metallic matrix. Imagine a stained glass window made of space gems and metal. These are thought to have formed at the boundary between the metallic core and the rocky mantle of a differentiated asteroid, offering a unique snapshot of this crucial interface inside a developing world. The other subgroup, Meteorites, are breccias, meaning they are jumbled up rocks made of broken fragments cemented together. They likely formed from the violent collision of two asteroids, where molten metal from one mixed with solid silicate fragments from the other, preserving a record of the chaotic, impact-rich environment of the early solar system. So we have all these different types of time capsules, but how do we actually read the time on them? The answer lies in radiometric dating. This technique relies on the fact that certain isotopes of elements are unstable. They undergo radioactive decay, transforming into more stable isotopes at a perfectly predictable rate. This rate is known as the half-life, the time it takes for half of the parent radioactive atoms in a sample to decay into daughter atoms. By measuring the ratio of parent to daughter isotopes and knowing the half-life, scientists can calculate how long it's been since the mineral closed, locking those isotopes into its crystal structure and starting the clock. The gold standard of these techniques is the uranium-lead dating system. It's incredibly robust because it uses two separate decay chains, uranium-238 decaying to lead-206 with a half-life of about 4.5 billion years, and uranium-235 decaying to lead-207 with a half-life of about 710 million years. Having two independent clocks in the same sample provides a built-in cross-check, making the results highly reliable. The data is often plotted on what's called a Concordia diagram, which helps scientists determine not only the original age of the rock, but also if its clock was ever disturbed by a later heating event. Other methods provide further cross-checks. The argon-argon technique, an improvement on the older potassium-argon method, is particularly clever. It allows for something called step heating, where a sample is heated in increments. The gas released at each temperature step is analyzed, which can reveal a detailed thermal history of the meteorite and distinguish its original formation age from later impacts. The rubidium-strontium system, with its very long half-life of nearly 49 billion years, is excellent for dating extremely old rocks and uses a method called the isochron technique. By analyzing several different minerals from the same rock, it can determine the age without needing to know the initial amount of the daughter isotope, which removes a major source of uncertainty. Using multiple, independent dating methods like these gives scientists immense confidence in their results. When they all point to the same age for a meteorite, we know we're on the right track. Now, within this meteorite family, some components are even older than the meteorites that carry them. These are the absolute oldest things you could ever possibly touch. First are the calcium-aluminium-rich inclusions, or CAIs. These are small, light-colored specks found in the most primitive chondrites. They are made of minerals that condense from a gas at extremely high temperatures, meaning they were the very first solids to form in our solar system. Using the precise uranium-lead method, the age of CAIs has been pinpointed to between 4.567 and 4.568 billion years ago. Since they are the oldest known solids formed within our solar system, their age is what we use to define the age of the solar system itself. But it gets even wilder. Meteorites also contain presolar grains. This is literal stardust. These microscopic grains, often just micrometers in size, originated in stars that lived and died before our sun was even born. They were created in the outflows of red giant stars or the explosions of supernovae, drifted through interstellar space, and were eventually incorporated into the molecular cloud that collapsed to form our solar system. We know they are presolar because their isotopic compositions are completely alien. The nuclear processes in their parent stars created unique isotopic fingerprints that are wildly different from the material that makes up our solar system. Some of these presolar grains, found in the Murchison meteorite, have been dated to be as old as 7 billion years, making them the oldest solid material ever found on Earth. With these precise ages, we can construct a detailed timeline of the early solar system. It all starts at 4.567 billion years ago, with the formation of CAIs. Within the first few million years after that, chondrules formed and the process of accretion was well underway, building the first planetesimals, the building blocks of planets. Evidence from iron meteorites shows that some of these planetesimals grew large enough to differentiate, forming metallic cores, within the first 1 to 2 million years. The giant planets, Jupiter and Saturn, formed relatively quickly, within about 10 million years. The terrestrial planets like Earth took longer, forming through collisions of smaller bodies over tens of millions of years. Our own moon is thought to have formed from a giant impact around 90 to 100 million years after the start of the solar system. This was followed by a period of intense violence known as the Late Heavy Bombardment. Between about 4.1 and 3.8 billion years ago, when shifts in the orbits of the giant planets sent a blizzard of asteroids and comets careening into the inner planets. The heavily cratered face of the moon is a lasting scar from this chaotic era. Finally, this all connects back to us. The study of meteorites offers profound insights into the formation of our own planet and the emergence of life. Carbonaceous chondrites, rich in water and organic molecules, support the hypothesis that the bombardment of early Earth by asteroids and comets delivered a significant portion of our planet's water and the raw chemical ingredients necessary for life. The isotopic signature of water in Earth's oceans closely matches the water found in these meteorites. Finding amino acids, the building blocks of proteins, inside them is a powerful clue that the materials for life came from space. So, the next time you hear about a meteor shower, remember that these are more than just shooting stars. They are fragments of creation. They are our most powerful tools for peering into the deep past, telling us when our solar system was born, how the planets were built, and how the stage was set for life on Earth. Through the precise language of physics and chemistry, these fallen stars continue to reveal the grand, epic story of our cosmic origins.